Hello, good evening. Okay, nice. So I can see that you can hear me. That's good. So let me see how many students have joined the lecture. Okay, so 20, 22, now 24. So shall we start? Let's not wait for the rest of the students because, well, we're going to have two extensive topics today, and so let's just not waste time. Let me switch on the presentation. Mhm. So we're having, as you know, we're having two lectures today, and I decided to split this evening into two different topics. Both of these topics are related to the coupon bonds markets. However, they are quite different because I decided that if we have the same topic for the whole evening, that would be too tiresome, probably even too boring. So let's discuss two different topics related to the coupon bonds market today. And we will start with something which is called pricing consistency or price consistency, or you can say consistent pricing, the way you like. Anyway, so what is consistent pricing and why it is so important? First of all, let's discuss what is consistent pricing. And I will move to the next slide right now. And I will switch on the marker. So in the upper parts of this slide, you see two formulas. So these two formulas are given to value a coupon bonds, a government's coupon bonds. So this is our first approach, which I call linear approach, because here we have only linear operators. And this is our second approach, which I call nonlinear approach, because here we have something nonlinear. For example, we raise to power, and this is a nonlinear operator. So both these approaches can be used to value a coupon bond. So obviously they should give us the same price. It's just a matter of convenience and a matter of a situation where you can use one approach or the other approach. But if you look at these two approaches and try to compare them, then you will see that in addition to linearity and nonlinearity, there are there is one more very important distinction. If you look at the second approach, you see that the major elements here in this formula is the yield to maturity. So we can say that this approach is built on the yield to maturity. If you know the yield to maturity, then you can easily calculate the coupon bonds price, because the rest of the information, the rest of the inputs is given. Coupon is given, face value is given, time to maturity is given. So yield to maturity is our, let's call it basic. What's going on? Let me erase this. So we can say that this is our basic building block for the non-linear approach. And if you look here, then we can say that here the basic building block is discount price, because if we know the discount price, actually a set of discount prices, then we can say that we can easily calculate the coupon bonds price. So pricing consistency can be demonstrated using this formula, the linear approach. You see that here we have essentially two different prices. This is a price of a coupon bonds, and this is a set of discount prices. That is, this DT belong to a discount bonds market, and BN belongs to a coupon bonds market. So we see a connection between two very important segments of the government bonds market, coupon bonds markets and discount bonds markets. And we see that whatever happens or occurs in the discount bonds markets, that is here, influence what occurs in the coupon bonds markets because of this consistency relationship. So we can say that this is a kind of consistency relationship. So with this formula, we draw a connection between a discount bonds markets or a discount bonds segments and a coupon bonds segments of the same treasury bonds markets. So this is really important. If price consistency, so if this formula holds, then we can say that price consistency exists in these treasury bonds markets. If it does not hold, if we say that pricing consistency does not hold, does not exist, then essentially we get pricing anomalies, meaning that in a certain way we just see that this just does not occur. We can say that this equality does not hold, therefore we can say that a discount bonds market evolves in its own way and a coupon bonds market evolves in its own way. This is definitely something very abnormal because it should not be like that. And if it occurs, we simply say that there is no pricing consistency, and if there is no pricing consistency, then there are pricing anomalies. Sometimes these pricing anomalies gives rise to arbitrage opportunities, but not always, because arbitrage opportunities occur when you can exploit pricing anomalies, but at the same time you get profits. You know that in order to implement an arbitrage strategy, you need to you will incur transaction costs. So if price anomalies are less than the value of the transaction cost, then there will be no arbitrage opportunities. So we cannot say that each pricing anomaly results in an arbitrage opportunity, but sometimes it occurs. So we're going to talk about pricing anomalies today, and essentially we say that if there is pricing consistency, there are no pricing anomalies, and if there is no pricing consistency, then it means that somehow pricing is anomalous in the coupon bonds market. So that's what we're talking. That's the topic of today's lecture, the first lecture. And so let me. I guess this was an introduction. Let me move to the next slide. Sure. How do you understand whether there are pricing anomalies in the markets or there are no pricing anomalies? So let's assume that we move back into the past, probably somewhere in the 1970s. As I told you before, 1970s, the first approach, this one, the linear approach, it had not existed. It was invented somewhere in 1970s. So only this approach, the second approach, had been used at those times because it was it had been offered much earlier. So at those times, somewhere in 1970s, only this approach had been used, and therefore, in order to understand if the coupon bonds was mispriced or fairly priced, what would you do as a financial analyst? You would calculate or estimate fair yield to maturity and compare it to the actual yield to maturity, and then just decide if this fair yield to maturity is equal to the actual or observed yield to maturity or not. So if there was a kind of consistency between these two yields, then we could say that the coupon bonds is fairly priced. If not, then the coupon bonds was either the coupon bonds was mispriced, either overpriced or underpriced. Anyway, at those times, financial analysts look at the yields to maturity. But the yield to maturity is a function of two variables. Indeed, again, if you look at this formula, you see that if we, for example, change the size of the coupon, then we hold all other inputs the same, unchanged, then you'll see that yield to maturity will change as well. And if we hold all inputs unchanged, but we change time to maturity, then yield to maturity will also change. So we can say that yield to maturity is a function of two variables, size of the coupon and time to maturity. Therefore, if you as a financial analyst want to represent graphically this dependency, then you would have to use a 3D space. So for example, you draw this system of coordinates, something like that. And so, for example, along the vertical axis, you measure y, yield to maturity. Along one horizontal axis, you measure, for example, size of the coupon, and along the other horizontal axis, you measure time to maturity. So anyway, you would have to use a 3D space and therefore a 3D modeling. So as a result, in a 3D space, you would get a kind of surface. So they used to call it yield surface. So that was a set of all yields which were fairly priced. So if you take all this yields, you will get a surface. So assume that you observe this surface. All well, I will not draw surface because it's really difficult to do it in this coordinate system. But anyway, assume that you are a financial analyst. You know that all the yields, fair yields, should be located on this surface. And now assume that you see that one actual yield from one real coupon bond is located above the surface. So what recommendation would you give concerning this coupon bonds? And this is my question to you. So as a financial analyst, what's recommendation? What would you recommend in this case? So a coupon, a yield to maturity lies above the surface. So it's definitely mispriced. In what direction? So underpriced. Well, this is true because the yield is above the surface. That is, the yield is too high, unjustifiably high, and therefore the price is too low, unjustifiably low. Recall there is an inverse relationship between the yield to maturity and the bond's price. And what recommendation would you give in this case? You know, financial analyst gives recommendations. Right, you would recommend taking a long position in this particular case, and then hopefully those who would take this long position would wait for convergence, that is, when the price will correct itself or when the markets will correct the price. So the price should go up, and hopefully that will happen quite soon. If this is a liquid markets and efficient markets like the majority of governments bonds markets in Europe and in North America, then in this case this conversion would occur quite soon. Okay, so it all was fine. However, at those times, this 3D modeling was considered to be quite advanced. And anyway, so that's indeed required some work to obtain this surface. This okay, there's someone. Well, you know, the market, well, it's a very difficult question about market efficiency. I would say very ambiguous. But right now we can, the general axiom nowadays is that markets are efficient. However, it does not mean that we always assume this perfect efficiency. Markets are always efficient. I mean, at least in the developed markets, but at the same time, they always produce a little bit of inefficiency which exists for a very short period of time. So that's what we consider to be efficient, meaning that generally they are efficient, but there is always room or opportunity for short-lived inefficiencies. This is something which makes markets alive. Otherwise, it will be just that. Okay. Well, that's a very important topic, and it's just not difficult. It's difficult to answer it in one question only. Okay. So what I was talking about, yield surfaces. So at those times, modeling such a surface was quite a tough job, but it was done, and that was a routine practice. Anyway, when this linear approach, I mean this one, this one, when this linear approach appeared, this yield surface practice just disappeared, I would say, simply because finding pricing anomalies using the linear approach is much easier than finding pricing anomalies using yields-based approach. Why so? Because you see, yield to maturity is a function of two variables, but the discount price is a function of only one variable. It's always much easier to model something using a function of one variable than using a function of two variables. Now tell me please, dt, it is a function of one variable. Which one? So we can say that dt is a function of one variable, and this is being right, time to maturity. Yeah, so this is correct, time to maturity. So generally, it is considered then modeling something using only one independent variable is easier than when you have two independent variables as inputs. So this approach is really easier, and if you try to find something like yield surface now, okay, for example, you can Google for it. You will not find a single yield surface even as an example, because this is just, this all was left in the past. That just does not exist anymore. You can find yield surface in Google in images, for example, but that will be quite a different yield surface, not the one which I was talking about. So this yield surface just has not been practiced since 1970s. So you won't even find a single representation of this yield surface even as an example. Again, because this linear approach is much easier to use to find pricing anomalies. So how we are going to detect pricing anomalies? First of all, we will add some error term here, because indeed, if there is no error term, then we can say that pricing is consistent. That is, we have a perfect and very clear relationship between the discount price and the coupon bonds price. So in order to allow for pricing anomalies, we will add an error term. It can be either positive or negative. When it is positive, it means that we have overpricing, because BN, the price of a coupon bonds, is larger than it should be. So we have overpricing, and then if you are a financial analyst, then your recommendation would be to short sell. And if the error term is negative, then we have underpricing, and therefore you would recommend taking a long position in this particular coupon bonds. So obviously this is much easier than drawing all these yield surfaces. However, there is just one problem about this linear approach, which should be solved somehow, because without it, this linear approach just does not work. So what problem is that? In order to understand if this price anomaly exists, that is, you are going to calculate fair price to compare it to the actual price, you first need to calculate the fair price. But you see that in order to calculate the fair price, you need to obtain dt, not just only one dt, but a set of dt, as many dt's as there are payouts made by the bonds. So for example, if bonds pays within the next 5 years, twice a year, then you need to get 10 discounts prices for corresponding maturities. So the problem is that some discounts prices might be absent, might be missing. So what to do in this case? We have a gap, a kind of a gap, and here is an example. Let's let's look at our markets. I mean, the government's markets, the markets for OFZ. This is the Russian government's bonds market, so OFZ markets. Tell me, please, do we have discounts prices for OFZ for this market? Right, indeed, because there are no discount bonds or well discounts OFZ, if it's possible to say so. So the Russian Federation used to issue discount bonds, but you all know what was the results of this issuance. Recall what happens in 1998. So after that, so all of those which have been issued since then, they all pay coupons. So we do not have discount bonds for either maturity, for any maturity. So that means that we don't have discount prices at all. Not that we have just a gap in discount prices, we just don't have discount prices. Then the question is how to implement this approach if we do not have discount prices. So this is just an example, and now an example of missing discount prices. And before we move further, let us study two very important concepts concerning the coupon bonds markets. They are related to this problem that discount prices might be missing. And these two very important concepts are term structures. So we have two types of term structure. I will move to the next slide now. Okay. So we have zero coupon term structure. So this term structure is built based on zero coupon bonds or discount bonds. And also we have coupon term structure, and this term structure is based on coupon paying bonds. So I guess there is no need for me just to repeat what is written here. So these are definitions of the two term structures. So I'll give you 30 seconds. Please read these two definitions yourself, and then I will continue. Okay, so at first glance, that might sound a little bit confusing, but everything is quite clear here. So we just make a note on the dates when the coupon payments from all the coupon bonds in the market falls, and after that we just see if there is either a discount bonds which matures on that day, and this relates to the zero coupon term structure, or coupon paying bonds which matures on that day, and this refers to coupon term structure. Here I make I introduce one adjustments, well, not adjustments, clarification that in case of a coupon term structure, we expect that on each date or each day when a coupon payments falls, there should be only one and no more than one and no less than one, so precisely one coupon bonds that matures. Well, why so? If less than one, meaning zero, then it means that we have a gap in the term structure. So in this case, we have incomplete coupon term structure. But if we have more than one coupon bonds that matures on that date, then there will be another problem, another issue, big issue actually. But we will talk about this issue when we will discuss arbitrage, theoretical foundations of arbitrage, and that will not be today. That will be, I guess, next lecture. Anyway, so what we have here, we have a zero coupon term structure, which is complete if for each date on when coupon payments falls, we have a discount price. So if this is so, then there is no problem in reconstructing this coupon bonds price. So we just take all discounts prices which we need and constructs the price of a coupon bonds. So we do not have any gaps, we do not have any discounts prices missing. In this case, there is no problem in obtaining the fair price of a coupon bonds. So if this is not the case, then our zero coupon term structure is incomplete. So there are some gaps instead of discounts prices. So if we have incomplete zero coupon term structure, this is not a big problem as long as we have a complete coupon term structure. So if we have this. So why this is not a big problem? Because if we have complete coupon term structure, then you can actually kind of reconstruct or fill in these gaps in the incomplete zero coupon term structure based on this information, on the information from the complete coupon term structure. Well, you might ask how, what's the methodology for filling in these gaps? So this methodology is given in, will be given in the reference. So I think it's just very nicely described by Campbell. So I will give you a reference to the Campbell textbook. This is a really easy methodology. So you use the data from complete coupon term structure and you use a bootstrap approach, or well, yeah, I think it should be called bootstrap and iterative procedure as well. So it's really easy, and if you are interested, then you just will read this this chapter 10, I think. So anyway, we will not spend time on this. We will move further. So assume that, okay, if there is a complete coupon term structure, you can easily reconstruct, you can create complete zero coupon term structure. However, if this is not the case, that is, if we have incomplete coupon term structure, so if we have this situation, then that's the problem, because in this case we cannot reconstruct zero coupon term structure and we have discounts prices missing. So now let's try to evaluate if this is a big problem for us in real life, in real government bonds markets or not. So tell me please, what do you think when we're talking about discounts bonds markets? Do you think well, we're talking about the world in general. So do you think discounts bonds markets are incomplete or complete? What's your opinion? If you cannot make an assessments all over the world, consider the UK as an example. We already studied UK in the first tutorial, so you got this Excel file from the debt management office, so you might say something about whether the UK has a complete or incomplete zero coupon term structure. So at least those guys who prepared these home assignments, definitely you can make some assessments. So no ideas. Do we have there are some gaps in discount prices or not? Discount prices are the same as trips. So okay. So okay. It was between zero coupon complete and incomplete, or zero coupon and coupon. So okay, I guess it's about between zero coupon and coupon. So in both cases, we look on the dates when coupon payments falls. So we take all the coupon bonds which are traded in the markets from the nearest maturity to the longest maturity, and we we choose all the dates on which they pay coupons. So we have a set of dates. I would say a set of dates which we can, I don't know, arrange in a chronological order. And then we see if on these dates a coupon bond matures or a discount bond matures. So if on these days a discount bond matures, then we can build zero coupon term structure. And if there is a coupon bond which matures, then we can build coupon term structure. So essentially the question is, can we have for each such date when payments falls? So can we have for each such dates discount bonds maturing on these dates for all of these dates without any gaps, without any, missing prices? If we do have this, then we can say that we have complete zero coupon term structure. And if we can say the same for coupon bonds prices, if for each such dates we have coupon bonds maturing, then we can say that we have complete coupon term structure. And then my question is, these are kinds of, okay, theoretical arrangements, but that is also what we have in real markets. For each markets, we can say that there is zero coupon term structure and coupon term structure. But now the question is, are they in the majority of markets complete or incomplete? And my question to you is, let's discuss the UK, for example. Okay, probably it will be even easier. Let's discuss the Russian Federation garment markets of OFZ. So what can you say about its zero coupon term structure? How would you describe the zero coupon term structure for the Russian OFZ markets? Complete or incomplete? Okay, so you assume that it is so Dmitry assumes that it's complete, and Ilya says this is incomplete because we don't have. Well, that's the correct answer, indeed, because recall what we discussed a couple of minutes ago. No, not a single discount bond. So it seems that it's not that we just have some gaps. We have gaps along the whole term structure, just not a single discount prices is available. So therefore, definitely in our case, the market is incomplete. Not the markets, the term structure, zero coupon term structure is incomplete. Now let's take this is a very obvious case because we don't have discount bonds market, so its term structure is incomplete. Let's take a case which is not that obvious. Let's consider the UK. So recall that you worked with this file, Excel file. You worked with the strips. So definitely we do have discounts bonds in the UK, and there are lots of discount bonds if we say that discount bonds are the same as strips. So in this case, can we say that the UK zero coupon term structure is complete? Well, yeah, that's indeed so difficult. Okay, I would say it's this way. Indeed, if you work with this file, you could see that there were lots of discounts prices strips, and there were March strips, December strips, June strips, and September strips. So quite a lot of strips, and essentially they represent discount bonds which are obtained from cutting coupon bonds into coupon payments and face value repayments. Therefore, on one hand, it might seem that the UK has complete zero coupon term structure because there are lots of discount bonds which mature each December, September, March, and June. However, well, however, I think it was about 5 years ago that the UK decided to issue very long-term bonds, coupon bonds. I think they would mature in 50 years or even 55 years. And for these bonds, so these bonds, when they were issued, they were not cut into strips. Therefore, what we have very long maturing coupon bonds. That is, for example, we will get the last coupon in 50 years or in 55 years. And for these particular coupons, there are no strips. There are no strip securities. Therefore, there are no discount bonds. It seems that in this case, we can say something like that. In a medium term, or probably up to, I don't know, 30 years, the UK zero coupon term structure is complete indeed, because there are lots of coupon bonds and most of them are stripped into discount bonds. However, if we go to the long end of the term structure, then we can say that in this case, the term structure is incomplete because indeed for coupon which will fall in 50 or 55 years, there are no strips which are traded in the markets. Something like that. Okay, let's now move to complete or incomplete coupon term structure. So this one. And again, I will ask you the same question. So what's about this structure? What do you think? Does the UK have a complete or incomplete coupon term structure? Again, you can refer to that file, or I don't know, it can be just your guess. Yes, so it's just like you said, we can observe some gaps somewhere at the long ends of the term structure. But this is about zero coupon term structure. Now my question is about coupon term structure. So what do you think? Can we say that in the UK has complete coupon term structure? Okay, so recall that again from that file which with which you worked, recall that you could observe strips which matures September, March, each September, March, or each December, June. Therefore, we can say that so we have two coupon paying cycles there, and therefore, essentially we have four coupon dates or four coupon dates each year: the 7th of March, the 7th of September, the 7th of June, the 7th of December. So if we want to have a complete coupon term structure, so we already know that 4 times a year we have coupon payments which fall on this, on these 4 dates. And therefore, if we want to have complete coupon term structure, we must have one coupon bonds which matures on each of these dates. So essentially, we need to have 4 coupon bonds which mature each year. one coupon bonds matures on the 7th of March, the second one matures on the 7th of June, etc. So tell me, please, is it possible to have 4 coupon bonds maturing each year? So do I correct understand that's when coupon falls in complete subtraction in order to. So what do you mean when you say equivalent bonds? In fact, it uh, it doesn't actually mean that we have just the same the repetition of one bonds after another. It doesn't. So it's not about the parameters of the bonds. Coupon bonds might be quite different in their parameters. For example, the size of the coupon. It's only important that there is a bonds, any coupon bonds, a large coupon, small coupon. But it's really important. What is important is that coupon bonds matures on the day when a certain coupon falls, coupon payments falls. Okay, so I'll just come back to this question. It's about the UK. So in fact, places highly unlikely that any country pays makes coupon that any country has coupon bonds maturing 4 coupon bonds maturing each year. This is a very large frequency, I would say. So if you look at the UK, again, you can just refer to this Excel file. You'll see that indeed coupon payments fall 4 times a year. However, coupon bonds matures once a year or probably twice a year. Sometimes there are even years in the history, not quite far away history, when there were no coupon bonds maturing in that particular year. So obviously the frequency of coupon payments is much larger than the frequency of coupon bonds maturity, or therefore it just not possible to have complete coupon term structure under these conditions. But tell me, please, what do you think about the USA? So the USA is the largest issuer, government's issuer. It's the first one, and there is a big gap between the volume of the first largest issuer, which is the USA, and the second largest issuer, which, as far as I remember, is Germany, but I'm not sure. But what I'm sure about is that there is a big gap because I saw this data. So tell me, please, about the USA. Does the USA have complete coupon term structure? So each date when there is a coupon payments, there is also only one coupon bonds which matures. So what do you think? Well, um, kind of, in a sense that indeed, if you look, let me just say it like that. For the rest of the world, no other country, even developed economy, so no developed economy, no other country has a complete coupon term structure. The USA is a kind of exception because it indeed has a very huge government bonds market. I would say that it's amazingly has a complete coupon term structure in the short term and medium term. If you look at the long term or long ends of the term structure, it will be incomplete. However, it's already a big achievement, and it's a really amazing thing that over a medium term, its term structure, coupon term structure, is complete. You will not see something like that for the rest of the world. It's only about the USA. they issue more debts, but again, the frequency more. Well, that's what I said, surprisingly, but they do have complete coupon term structure. Well, you will be actually surprised. They have more than complete. That is what I say. They sometimes they even have two coupon bonds maturing on each date when the coupon payments falls. But that's this occurs on very rare occasions. But generally in the medium term, they have complete coupon term structure. Later on, well, if I have time, not today definitely, I will tell you why this is so important. But essentially, it's all about hedging techniques. You either hedge linearly or non-linearly, and if you have complete coupon sum structure, then you will be able to hedge using linear techniques, which is much easier again than using non-linear techniques. Well, but that will be said, that will be discussed, I guess, in the next lecture, not today, not this evening. So anyway, now we see that except for the USA, the rest of the world has a kind of issue with this complete or incomplete zero coupon sum structure and coupon sum structure. So essentially, we cannot find a single country except the USA where we can obtain all these DTs, the one which we need, just simply because they don't. There are some gaps, either like in Russia, we don't have DT at all, or there are at least some gaps. So what to do in this case? If this is so, then essentially we cannot reconstruct the fair coupon bonds price, and therefore we will not be able to detect pricing anomalies. And therefore, if not like this, then we really don't know if there is pricing consistency in the markets or there is no pricing consistency, because we just cannot detect any pricing anomaly because we do not have enough discounts prices. So this problem has long been recognized, I think, just from the very beginning when DT appears, when this approach appeared. At those times already, well, I think this research into discount function already was already started. So our major problem is that some discount prices are not known to us, are unobservable in the sense that we would like to have them, but they just don't exist. So what to do in this case? Then there was a series of research papers to tackle this problem, and nowadays we have an established approach to solve this problem, to obtain discount prices. And that's what we're going to do. That's what we're going to study in this lecture. We're going to look how central banks well, tackle this problem and how they reconstruct discount prices. But before we look at one particular approach, let's look at the problem generally. So what you see here, this this blue curved line, I constructed this line using Excel, and what I did, I downloaded the same data from the data management office, the one for the same dates which I asked you for which I asked you to calculate to download data. And then I took discount prices, essentially prices of strips securities, which matures in different years, so 2005, 2006, etc. So I then just plotted this this curve, meaning essentially these are just dots, points or dots. I guess we should call it dots. So for each time to maturity, there is a certain strip with a certain price. So we see, and then there will be some dots, and then I just connected these dots with a line. And essentially, what we see here, we see dependency of a discount price upon time to maturity. So that's what I just wrote here. So this one. So dependency of a discount price on time to maturity. And as you can see, as a result, we get a downward sloping curve, which seems to be quite logical. So it's downward sloping, but what is very important about it is that if we have such a curve in for real government bonds markets, then it's not at all a problem to reconstruct any coupon bonds price because all discounts prices so seems to be available for us. So I can arbitrarily choose any time to maturity, and then I just immediately can say what is the price, discounts price for this time to maturity. So that's what we would like to have for a government bonds market, this kind of curve. And this is what is done by central banks, including the Russian central bank and the Bank of England, the Federal Reserve, which is the central bank in the USA. So all these banks, they produce this curve. And this curve has its name, so it's called discount function. Essentially, this is a function of discounts price, but we don't say, it's time consuming to say it like that, so we just say discounts function. So we denote it like that, d, because of discounts price, t, so d is our dependence variable, t is time to maturity, and this is our independence variable, and beta is just a set of parameters. As you understand, any function should be featured, or the majority of function should be featured with a set of parameters, and therefore here we have a vector. This is a vector of parameters. So for you to understand it better, tell me please, how many parameters do a linear function have? So we have linear function, and how many parameters does it have? Well, Anna is correct, 2. No, 3. So there is also a version with 1 parameter and 3 parameters. Well, 2, precisely 2. So will you tell me, Anna, which one? How do we call them? TB. No, not TB. So indeed there are 2 parameters, but how do we call them? So there are 2 coefficients. Parameters or coefficients, the same. So, well, x and y are independent variables, but the parameters are, is the name of the parameter. Okay, now recall school math. I'm just talking about a linear function. It's not about time to maturity and price. It's just recall linear function from right. So how do we call this alpha or a and b? Coefficients. What kind of coefficients? So a, right, okay. So constant and slope. So b is slope and a is a constant, or sometimes actually we say intercept coefficients and slope coefficients. So that's what I'm talking about. The majority of functions can be and should be described by a set of parameters. And in case of a linear function, we have 2 parameters, but now I do not say what kind of function is that. We just say that there also will be some sets of parameters which will describe this discount function. And what we're going to do, we're going to reproduce or reconstruct this discount function. But before we do this, let's look at one very important aspect concerning the discount function. The discount function, like for example, the way I calculate, well, the way I build it here, okay, I get something like that. So this is our discount function for the UK treasury bonds markets. However, this is an approximation only because I approximated the discount function using strip prices. But the real discount function is unobservable. We already know that this is just a dependency between the discount price and time to maturity. what kind of dependency, what precise mathematical formula describes this dependency is not known. It's this is how we say discount function is unobservable. This is pretty much the case for a lot of economic variables or economic phenomena. For example, we know that one economic variable is dependent upon another economic variable. So we can say that there is a kind of economic dependency, but we don't know mathematical dependency. We can only say that there is economic dependency. And then we try to approximate this dependency using, for example, econometric model. So econometric model is only an approximation. The precise mathematical dependency is not known. In our case, this is the same. So we know that there is a kind of discount function, but that's it. We don't know the precise mathematical representation for the discount function, and therefore we will approximate an unknown, unobservable discount function with a function which is very well convenient for approximation. So in mathematics, usually there are two, I would say, working horses, two functions or two which are used as working horses for approximation. So if you know mathematics well, tell me please, what mathematical functions do we use to approximate other functions? Okay, no ideas. All right. Um, um, tangency. Is that, well, using tangency, you can approximate something about the points, but not the function itself. I guess derivative means the same as, like, tangency here in the same sense. So no, I'm talking not about evaluating a function at one particular point. I'm talking about approximating the function itself. So in fact, these two functions are either polynomial function or well, exponential functions. So two functions are most frequently used in order to approximate something which is unobservable. And that's what is done by central banks. So they use polynomial function in order to approximate the discount function, which is unobservable. But whatever methodology they use, we know for sure what we can expect from this function. So whatever mathematical formula we will get as a result, we know for sure that there should be three features, three properties of this discount function, which we must observe. And the first property is that, well, the first property, as you can see, this function is downward sloping. So it has a negative slope, so it's downward sloping. And this is something which we will definitely expect from a discount function, whatever way we approximate it. So tell me please, why do we expect that any discount function, any version of a discount function should be downward sloping? So downward sloping means that there is a, well, this dependency is, how to say it, inverse or negative. So anyway, as time to maturity increases, discounts price decreases. So what do we expect this? But why? Why do we expect negative relation? Yes, this is formula. I would like just you to say. I would like you to say it's not from the point of view of mathematics, but from the point of view of the reason. So why do we have a reason to assume that there will be this negative relationship? Why? Why don't they increase? So recall what we discussed in the very first lecture. Also, the previous version, because value of money, right? And now, will you tell me why value of money reduces? Reduces. No, this is not about price risk. So value of money. And now, finally, the fundamental reason why there is value of money. No. So recall what we discussed in the very first lecture, that everything can be explained by human psychology. I mean, at least in pricing. And we assume that money today is more expensive than money tomorrow simply because, well, this time it's not about uncertainty, but because of, okay, probably uncertainty, but how did we call it last time? So following Irving Fisher. Right, that's what I wanted to hear. So mortality and actually also poor imagination. So purely psychological features are inputs into this dependency. So this dependency can be explained by purely psychological features. So time impatience, because people are mortal, they might suddenly die, or not suddenly, but anyway, and they have poor imagination. This is something so basic that under no condition would we expect any other shape than this one. So the discount function should always be downward sloping, because otherwise we would have to agree that people have some weird psychology, but this is just not the case. The majority of people think in the same direction. And therefore will always have the same shape, downward sloping for discount function, and no other shape. So this is the first very important moment. Second is that we would like the function would be continuous, in the sense that there should be no holes, because there should be no gaps, because there should be for any arbitrary chosen discounts, for any arbitrary chosen time to maturity, I would like to have a discount price, so there should be no gaps. Therefore, we ask for this function, we require for this function to be continuous. And also the third moment, it should be smooth, in the sense that it shouldn't go downwards like that, it should be smooth, no sharp upward movements, no sharp downwards movements, because essentially for a small increase in time to maturity, we should observe a small decrease in the discount price. Again, this is something very psychological, that can be explained by human psychology, because this is really unlikely that people think like that, that they should be something like that would be really weird. So let me see how much time we have left. Okay, we still have enough time. I think so. So let's move further. Today we will see how a discount function can be reconstructed, but I will give you a methodology which might be considered as a basis for what the Bank of England does. Mind is that there are essentially two different methodologies. Most popular in the the Central Bank of Russia uses another methodology, but actually this discount function is calculated by the Moscow Exchange for the Russian central bank, not by the central bank itself. So it's the Moscow Exchange. It was the Moscow Exchange who actually introduced this idea that we also should have discount function for the Russian Federation, for the Russian government's markets. And they used the Nielsen-Siegel methodology, and the Bank of England uses another type of methodology. And today we will look at it, but it's an easier version, much easier version, because the version which is originally used by the Bank of England is much more difficult, and that just, it's terribly outside the scope of this course. Anyway, you will get an idea of how it might be done. So we're going to approximate a discount function using a polynomial. Let's move to the next slide. Okay. So we already know that it's going to be downward sloping, continuous and smooth. And by the way, okay, the major difference between what we're going to do and what the Bank of England does is that we're going to take a key degree or k degree polynomial, and the Bank of England uses a spline function. So instead of a polynomial function, it uses a spline function. What is a spline function? It's actually a kind of polynomial, but well, if we look at this curve again, so we can divide this curve into, okay, let me erase all this because it's getting messy. So if you look at this curve, we can actually divide this curve into different segments. And then you will see that each segment has its own degree of curvature. So probably it will be more accurate to describe each segment using polynomials of different degrees. So that's going to be a spline function. But we're going to use just only one polynomial in order to reconstruct this discount function. This is much easier, and that's just what we can cover today. So we're going to use a key degree polynomial, and this polynomial looks like that. I remind you, for those who do not remember. So this is our k degree polynomial. This is its extended form, and this is its condensed form. So as you can see, this is simply a summation, and we have k plus 1 terms. So k plus 1 because we start with 0, so in total we have k plus 1 terms. Now, in this particular representation, we have x as independent variable, but in our case, the independent variable is time to maturity. So let's simply substitute t instead of x. So now I do not introduce any mathematical transformations. I simply replace x with t. Again, we have either extended form or we have condensed form. And now let's look at each of these terms separately. So you see, by the way, that we have beta 0 here, beta 1, beta 2, etc. So these are all our parameters, the one which we don't know, but these parameters describe our polynomial. And tell me, please, are these slope coefficients or intercepts? Or where do we have here slope coefficients and intercepts? So for example, the first term, okay, slope. Well, okay, all the coefficients are slope coefficients, but probably if you look at the first one, this one, I think it can be considered as an intercept because t raised to power 0 is, well, it's 1, so, and beta 0 is a constant, so we will get some constant here. So probably I mean, well, actually you're right, beta 0 is also slope coefficients, but if we consider the term altogether, then it might consider to be as an intercept. Anyway, so we can say that we have here betas as slope coefficients, but then let's look at t's. So betas are slope coefficients. What about t's? we have t raised to power to 0, t raised to power to 1, t raised to power to t, etc. So essentially, we can say that we have a simple function of time to maturity, that is time to maturity raised to certain power, and power ranges from 0 to, so here we have 0, here we have k. So how do we call this function in English? So t raised to certain power. So, and if you don't know how it's called in English, say at least how we call it in Russian. No. What I'm asking about, look at these terms individually. So t raised to power to certain power, right? This is called exponential function. Well, and no. Actually, it's not exponential. No. Well, any other versions? Look. So that's our function. X raised to power a. So it's called power function, simple power function. And in Russian, we say, as far as I remember, степенная функция. Anyway, so if you look at the polynomial, then we can say that our polynomial consists of a set of power functions, or we can say that the polynomial function is a complex or composite function, and this composite function has its simple components, and these simple components are power functions. So indeed, if you look here at this summation, then we can say that the polynomial function is essentially a weighted sum. What's the sum? We sum power functions, and what are weights? Coefficients, slope coefficients. So we weight power functions with beta coefficients or with slope coefficients. So essentially, a polynomial is a weighted sum of simple functions, and these simple functions are power functions, time to maturity raised to certain constants. So that's what I have already said. So we have a weighted sum of k plus 1 simple functions of time to maturity. So, and each simple function is time to maturity raised to certain power. So like that. And so we just can now be a little bit abstractive and just write it like that. So a weighted sum of simple functions of time to maturity, and these simple functions are power functions. Okay, so let's have it like that. Now, so this is the specification of the discount function, and now the question is, so okay, so we are going to use this specification to find dt, and now in order to find dt, as you can see, we only need to find slope coefficients because power functions are quite known. So you just count time to maturity. So from the nearest maturity to the largest maturity, this is easy. Now, as for k, you simply need to define to determine what degree of polynomial, okay, polynomial of what degree you are going to use. But this is something which will be defined not probably by you, but by the computer program. It's a matter of fitting model, and therefore this is something which is can be routinely done. So anyway, everything is given here except for these beta coefficients, slope coefficients. This is something which you need to know. You need to find somehow. So how we are going to find it? For this, we are going to use mathematical techniques and econometric techniques. And so I will start with mathematics, and then I guess we'll make a break, and then I will move to econometric techniques. So one slide will be very, very mathematical. So I would ask you just to pay your full attention to this. Oh, okay. This is not that slide. This is just an example. So, for example, if my computer program says that the optimal degree of the polynomial, the optimal degree is for our polynomial is 3, then I will get something like that. So my discount function would look like that. So 3-degree polynomial, and that's a representation. So the only thing which is probably interesting here, so look here, everywhere previously and in this slide as well, I count time to maturity starting from 1. So 1 period from now, 2 periods from now, etc. However, and here I also count from 1, but you know that t can actually be equal to 0 as well. So, for example, let me write it. So t must be equal to 0. You know that this is also kind of time to maturity. So this is the period 0. So time to maturity occurs right now, today. So I have the right just to write it like that, but I don't write it like that in this particular slide and previously as well. So I just cannot count, you know, I write t I count t from 1, not from 0. So tell me please, can I start counting time to maturity from 0 using this specification? So I use this specification for the discount function, and it seems that, so my question is, in this particular specification, can I start counting time from 0, or I cannot? Why do I write t is equal to 1 instead of t is equal to 0, 1, etc.? So just so when t is equal to 0, f of t, so this simple function is going to be equal to 0. So for example, let's start with a t equal to 0 in this line. So 0 raised to power to 1, 0 raised to power to t, etc. And now we have 0 raised to power to 0. So what do we have as a result if we raise 0 to power to 0? So Konstantin, you believe that we get 0? So Maxim believes that we get 1. So 0 or 1. Well, that's exactly the problem in mathematics. Half mathematicians believe that we will get 1 as a result, and the other half believes that we will get 0 as a result. So a general opinion is that let's decide that it's not well defined. So there is nothing like that. There is no 0 raised to power to 0. This is a mathematical convention. No. I mean, there is an opinion like that. I understand that it's, well, I think it's can be shown using limits, but still it's only an opinion. It's just not, it has not been proved, meaning that there is another opinion that it's going to be 0. So therefore, in this particular specification, this is just not possible to start counting with 0. We can start counting with 1, or we can start counting with any maturity more than 0. For example, we can start counting with maturity equal to one day, for example. We simply need to represent 1 day as a ratio of a year. But we cannot just, in this particular specification, we cannot count with 0. But in my home assignments to you, I will ask you to slightly redefine this discount function, this specification for the discount function, so that I could start counting with 0. So, and there will be no problem about, you know, this 0 raised to power to 0. So somehow it should be redefined, not drastically, just a little bit, but that will be a part of your home assignments. So I guess we can move to the next slide, but now we can stop here for a while. we will do now a little bit of mathematics. Well, first we will have a break, and then we will do a little bit of math manipulation with this discount function. So now it's, well, I have 8 minutes left. So 19:52. Okay, so let's have a break of 10 minutes and then we will continue. Okay, so let's continue the lecture. So we're a little bit out of time, running behind the schedule. So I will end this topic and then I will move to the other one. So now we need to make a little bit of math transformation in order to come to an econometric equation, because right now we simply have a formula. So here we have the discount function to the right, just how we define it. And to the left, we have this formula, the linear approach to value a coupon bonds. So we know that dt, discount price, can be obtained from discount function, from this one. So let's substitute this formula for discount function instead of dt into this formula. As a result, we have something like that. So we see that we have two summation sign here. So first we sum over all k's, and these are our degree of polynomial. And then we sum up over all t's, and t is the all the times to maturities which exist in this particular government bonds markets. Now, actually, what we can do, and this is quite possible to do in mathematics, we reverse the order of summation. So like that. So first we sum up over k and then we sum up over t, but now we sum up over all t and then we sum up over all k's. So we can do it like that, and as I said, this is quite possible to reverse the summation, the order of summation in mathematics. Now we sum up over all t first, and then we sum up over all k's. So if you look at beta k, then you know that beta k depends only upon k. So beta k is a slope coefficient, and therefore it's even if when we sum up over all t's, beta k just does not change because it does not depend upon t, it's dependent upon k. So therefore within the first summation sign, this is going to be a constant, and if this is a constant, then we just move it in front of the summation sign like that. So now we have beta k in front of the summation sign, and so we first sum up over all t's, then we multiply by beta, well, not multiply, and then we sum up over all k's. So let's look at this expression, which I highlight in square brackets, which I place into square brackets. So let's look at it a little bit in more detail. So I'll just have it like that. So recall that f of k is a simple function of time to maturity, and according to our specification, to the specification by the polynomial, f of k is power function. So this is our f of k, simply time to maturity raised to certain power. So this term, I would not say that it has any particular economic meaning, in a sense that we don't need to interpret it somehow economically. But if you want to interpret it in whatever way, then probably we can say that this is again a weighted sum. So because we sum up and this is a weighted sum, so this is CTN. As you remember, these are all payments, coupon payments, and the face value repayments from our coupon bonds N. So these are all coupon payments and face value repayments, and this is what we weight, and we weight whether this function. So if you want to have at least some interpretation of this term, you can say that we have a weighted sum of future payments which are weighted by powers of times to maturity. But again, this is just not necessary because this is simply a mathematical term. It's a little bit cumbersome, it's big. So let's just substitute, let's denote it with this letter, RK. So we know that RK is going to be equal to this term. Now let's look at this term once again. And tell me please, if we choose, well, one particular bonds, coupon bonds N, tell me please, is it possible for us calculate this term? I mean, is it possible to get, well, a particular numeric value for this RK? So for example, RK is equal to such a numeric value. So is it possible to calculate it? And this is my question to you. In a sense that do we have all necessary inputs, or there are, I don't know, something which you don't know, or we can calculate it? Okay, so no one has any idea. Okay, so once again, we're talking about one coupon bonds N. This is, okay, let's check. Right. So indeed, all inputs is given to us because if we're talking about one particular coupon bonds, then we know all its future payments. So this is not something which is not known to us, and we also know the time to maturity. The way how we are going to count time to maturity, because, for example, for the UK, we might assume that the time to maturity, the term structure starts with, I don't know, 0 period, for example, and ends with 55 years in the future. So, for example, if we take into account this long-term coupon bonds, which were issued with 55 years to maturity, then in our case, T will be equal to 55. So, and that means that everything is known to us. As for K, just as you asked, so did we estimate K? Well, right now we derive a formula, so we have not estimated K yet, but if you if you have ever tried to optimize, then using mathematical optimization, then you know that it's always done simultaneously. So K will be given to you immediately when you have all the necessary inputs. Or you can actually define K, pre-specify K in advance. For example, you strongly believe that K should be more than 2, because indeed, if you look here, it might be difficult to assume that this looks like a parabola. Probably you should have a higher order polynomial, but at the same time, you don't want to take a polynomial of order 100, because this is something really excessive. So in this case, you can actually have an expert estimate, as you say, as we usually say. So it depends. Anyway, so this can be calculated. So this is something which is, well, if you will calculate it manually, then it will take time, but we can easily calculate it using computer. So in this case, it will take just, it will be all calculated within 1 second. Estimating, minimizing residuals. Well, that should be taken into account. However, that's not it. The procedure will be more complicated because it should take into account not only residuals but also the expected shape, right? If the resulting shape will be the one which we don't expect, and we know that, for example, we expect a downward slope, and then in this case, or it will be a downward sloping, but it will have spikes, then this is also, so there will be additional restrictions on this optimization. Okay, anyway, so but the way how we are going to do this indeed, it's really simple. It's not that's what I'm talking about. It's the way how the UK, the Bank of England does it. So it's more complicated. But in our case, Well, k. But actually, I really don't know if the experts in the Bank of England use some pre-specified historically defined k, the one which they consider to be the most convenient, or they change k in each iteration. But it seems to me that they do not. That would be really weird. Anyway, so that's what we are going to have. So let's call it RK, and now let's just substitute RK instead of this big cumbersome term in the brackets. And then we have something like that. So for the nth bonds, we have this expression. Now that's it about mathematics, nothing more. Now let's move to the econometric parts. So I reproduced this equation here. So this equation is from the previous slides. Now tell me, please, does it look like an econometric equation? Yes, so looks like regression. And now the most, I would say this. So this question will show if you understand this equation well or not. Tell me, please, what is SLR? SLR. Okay, simple linear regression. Okay. So this question the answer will tell me if you understand this equation well or not. Tell me, please, is it a time series regression equation or a cross-sectional regression equation? So you say that this is time series, and so Zhao says time series, Daniel cross, Konstantin cross-sectional. Yes, you are all right. This is definitely a cross-sectional regression equation. So assume that we're at the end of business day and we collect observed prices of all coupon bonds which are traded on the market. For example, all the UK Treasury gilts. So we collect from, I don't know, market makers or the evening prices, close prices, for example. So this is going to be our explained variable, or we can also say that this is our regressant. I guess this is just regressant, another name. Now, and this is gonna be our explanatory variable. So RK is our explanatory variable, and there will be as many explanatory variable as the specification of our polynomial gives to us. So in our case, we specify k degree polynomial, so there will be k plus 1 terms like that. So it's not just cross-sectional regression, it's multi-factor, or well, first I should say cross-sectional and then multi-factor or multivariate regression equation. So for each coupon bonds, you know the observed price. So this is an explains variable. Now for each coupon bonds, you calculate this term. So that's what we discuss here. We can calculate it. It's really easy. And that's going to be an explanatory variable. And then beta coefficients in this particular specification are simply regression coefficients. And this is a very simple, just like the previous students said, that's going to be simple linear regression equation. So we can estimate these regression coefficients simply using OLS methodology. So ordinary least squares, and then you get these beta coefficients, estimates of these beta coefficients. And that is actually what we need to get. So recall that we specify our discount function as a function of time to maturity. So we count time to maturity. This is our independent variable, which we know which values it takes on. We count from 1 period, 2 periods, etc. The only thing which is not known to us of what slope coefficients should we put into our polynomial equation. And these slope coefficients are found in this linear regression. So note please this very amazing thing. We, in order to build a discount function in any market, for example, in Russian markets or in the UK markets, we don't require a single discount price. So it's quite possible that no discount bonds are traded at all in the markets. We don't care about this at all. We still can reconstruct a discount price using this mathematical and econometric technique. We only ask, we only require that coupon bonds are traded. And mind it, we don't require a complete coupon bonds term structure, because in all this methodology, it's nowhere is said that we require this completeness of the coupon paying bonds term structure, because this is just not necessary. We just need some discount, some coupon bonds. Well, the more the coupon bonds we have, the better, obviously, because in this case we have more precise estimates of beta coefficients, but we never say that we need complete coupon term structure. So that's an amazing thing. We get a full set of discounts prices from the coupon bonds markets. We don't ask for any discount price actually observable in the treasury markets, because it's quite possible that we don't have discounts bonds at all. No, so that's what is essentially done by the central banks. However, mind is once again that the methodology, the actual methodology, is more advanced than this one. Actually, this methodology was given by McCulloch somewhere in 1970s, so in his paper. But even in his paper, he used, even 50 years ago, he still used more advanced methodology than this one. But he was a pioneer of this of this reconstruction of discount function, which is now just a routine practice, which is done by the majority of central banks. So last year I had the students from Somalia, if you know Somalia. So he asked me a lot about this construction of actual discount function. I mean, using the more advanced methodology, because he wanted probably to implement it in for Somalia. I'm not sure if they have coupon bonds markets in Somalia, but I asked him, "What about your central bank? Does it? It does not. It seems that it does not construct a discount function." He said, "No, I just could not believe into that." And so I checked. I tried to Google for Central Bank of Somalia discount function, but indeed nothing like that. And he said that it's just because of Islamic finance. So they use this Islamic finance system in which discount function is just not applicable. However, he said that they tried to implement some European approaches in their country as well. And that's why he wanted to reconstruct this discount function there. Anyway, so I'm going to give you several examples of how it looks like. I used the data which were produced by McCulloch in 1970s. So I just why 1970s? No, I mean his first work on this was written in 1970s, but then he just provided well, us, that I mean us meaning all of students and scientists with this data which he got, and then I just used this data to construct some the discount function. So let's look how it looks like for the USA. So I just I took his data and I constructed it myself. So I'm going to use a 3D model in here. So later on there will be a 3D picture as well, but now 2D, two-dimensional picture. So this data, his data, I used to construct 11 discount functions. So here we have, if you count, we will have 11 discount functions. And these discount functions are given on one particular day. Well, usually discount functions are updated at the end of each business day. So update frequency is once a day. As far as I remember, there was some time in the future, not in the future, in the past, when the Moscow Exchange updated the discount function and the yield curve several times a day, but I don't think if they maintain the same high frequency nowadays, or probably it's just only once a day at the end of each business day, that's they recalculate the parameters, and the shape of the discount function changes as well. Anyway, here we have 11 dates, which are half year apart from each other, and so we have the span from 1985 to 1990. And as you can see, so for example, I want to find, so I don't know if I look at this discount function, I really don't know on for what date it is built. I don't remember. But if we have this discount function, and if I ask you what is the discount price for 15-year maturity, then you immediately tell me that it's going to be something about $0.20, which is 20 cents. So we can say that $1 paid 15 years from now costs 20 cents. But if we ask the same question about, this is 2 years, so if we ask about the same question for a 2-year maturity, then I will say that the price of 1 unit of money, $1 paid in 2 years, now this price is 80 cents. So as you can see, we do have the same shape as we expected, so it's downward sloping. It's smooth, well, kind of, except for this area. I don't know why we get it, but probably we have the skin here. I have the suspicion that this is because Macalech provides more data at the short ends than at the long ends. And anyway, it's kind of smooth, and it's continuous. So that's what we want to have. That's what we expect from a discount function. Now let's look at the same picture from a different perspective. So for example, we have different maturities here: 2-year maturity, 15-year maturity, I don't know, 27 years to maturity. And for each maturity, we have a discount price. But if we build a discount function for each day between 85 and 90, then for each maturity, we have a set of discount prices which just evolve from one day to another day. So let's look at this picture, and I will move to the next slide. Now it looks like that. So here I have again the same periods, 55, 91, and I have chosen several maturities, starting from 0-month maturity and ending with 20-year maturity. And now you see how discount prices for different maturities evolved over these periods. So you can see that there is a certain pattern. Let's start with a 0-month. Well, 0-month does not mean that it's just 0 periods to maturity. That's how Macalech denotes it, 0-month. However, does not mean that there is precisely 0 time, or that there is no time to maturity, meaning that it just matures right now. It actually means one day, or actually overnight. So overnight periods. That's what here. Because if it were just today, then this line, it will be just straight at the level of 1, because we know that discount price, which for the bonds which matures today, is strictly equal to 1. But you see that it's a little bit, it's not straight line. It still has some variation. So it only means that we have something like an overnight period, and this discount bonds corresponds, this discount price corresponds to an overnight discount yield or overnight interest rates. This is something which we in Russian we say, how do we say, it's учетная ставка, as far as I remember, ставка рефинансирования, something like that. In the USA we call it the federal funds rate, so this overnight rate. Okay, so obviously it's as you can see, it's volatility. The volatility of this discount price is the smallest one, but as we increase time to maturity, we see that the discount price becomes more and more volatile. And now my question to you: how would you explain that as time to maturity increases, the volatility of the discount price increases as well? So what could be an explanation?
Victoria, maybe the difference connected with amount of years which we are going to hold bond. Because of that, there are some changes in the function, like longer period, longer volatility, bigger volatility.
Okay, so right, longer periods. Let me also see that there are some messages as well. Expectations of economy change in different years, contraction, expansion risk, default risk. Well, I wouldn't say I wouldn't be so much specific about saying default risk or expansion. But might happen, but generally it's all about some. So okay, if you look at the first curve, it looks like straight line, but still it's a little bit of curve. So overnight discounts price corresponding to overnight interest rates. So what might happen overnight that is very unexpected? Well, nothing particular. I guess everything is quite expectable and transparent within a 1 day or one night period or overnight period. So we just don't need to adjust the discount price that much frequently for overnight periods. But if as time to maturity increases, we would probably adjust our expectations of this about the future more drastically because each time there appears some information which will influence these short-term periods and long-term periods, right? It will not influence overnight periods, definitely, but it will influence short-term and medium-term periods. Therefore, we will more frequently adjust our expectations, more drastically adjust our expectations, and therefore this all results in higher volatility of medium-term discount prices. But now look at long-term discounts price. This one, 20 years to maturity. You see that it's indeed also volatile, but it's a little bit less volatile than 10-year discounts price or 6-year discounts price. How would you explain this? Okay, definitely you might say that, well, you might think, and that will be just correct, that volatility is the longer time to maturity, the larger uncertainty. So it seems that the 20-year discount price should be even more volatile, but it is less volatile. Why? Okay, I guess there are no versions as an answer for this question. So when we're talking about such a long period of time, it's again lower liquidity, maybe the constitution versus likeness on the response. Well, no, it's all about again. It's about human psychology. So have you noticed how frequently I refer to human psychology? Indeed, we adjust our expectations about medium term, and therefore we adjust our prices, discounts prices, and source of information is limits. Well, Zhao is kind of right. Uncertainty is the main reason because the future is unknown. Well, it's about uncertainty. It's actually about our attitude to uncertainty. So we don't know what will happen within 5 years, 10 years, or 20 years, but we actually care more about what will happen in 5 years or 10 years and less about what happened in 20 years. Even though it is even more uncertain for us, we still care about it much less because it's really difficult to imagine uh, what exact situation will occur in 20 years. So this long term is less important for us because it's too uncertain. I mean, there's just no, it doesn't make sense to make any sensible predictions about what will happen in 20 years. You can make sensible predictions about a 6-year period or a 10-year period, but not 20-year periods. Therefore, and whatever happens now might influence what will happen in 6 years, in 10 years, but everything, all this is not really significant for what will be in 20 years. Therefore, these kinds of influences, the psychology influences discounts prices with a 10-year maturity, just less less adjustments to expectations because no one cares much about it. So that's an explanation. Now, let's unite this figure and this figure into one graph, and that's going to be a three-dimensional graph because we're going to use different time to maturities on one scale, on one axis, and also different dates on the other axis. So let's see how it looks like. So here we have a set of discount functions from 985 to 91, I guess. And these discount functions are extended from 0-month maturity to 25 years to maturity. So I would say this is a kind of discount function surface. So does it look like a waterfall? Or probably you have some other associations. You seem to have no associations. Okay. Anyway, if we, so we can actually make a slice over this figure. And if we make a slice along this axis, along the maturity axis, then we will just get one particular discount function for one particular date over all maturities. But if we make a slice over this axis, then we get something like that, this figure. Now, recall please that any discount price is connected to discount yield using this formula. That means that we can take all discount prices here and transfer them into discount yields. And then we get a set of discount yields, also a kind of surface of discount yields, just like we have surface of discount functions. And let's, so that's what I did, and let's see how the surface of discount yields looks like. So this is our surface of discount function, and then the other side of the coin is the surface of discount yields. So tell me please, if we make a slice alone, so again, here we have dates, here we have maturities. So if we take a slice along this axis, what we will get as a result? And this is my question to you. So you could, for example, look at this. It's already like a slice has been taken. So what is this? So think of what we have along the, so there will be no this axis, and essentially we have two axes only, maturities and yields. So these are yields, or no, expressed in percentage, in percents. So what we have the results? And we already have we discussed this figure or graph, if it's possible to say so. We discussed it some time ago, actually last week. So the economy is expected to be stagnant compared to 1985. Yes, but Zhao, can you just tell me how do we call this figure? That was my question about. So what's the name of this figure? What we're talking about? Okay, so this is called yield curve, right? Any single line like that is called yield curve, and that's what we were talking about last last lecture, I think. Last, no, not coupon yield curves. Actually, these are just yield curves. Recall that we're talking about discount functions. So we construct yield curves using this equation. So no coupon is given here. So this is purely a zero coupon yields. That's how we can reconstruct it. So we get discount function. We calculate discount function. And then we get, if we have a slice, we will get just yield curve. So essentially we have a collection of yield curves, US yield curves here from 95 to 89. And right, that's how you said something about, well, not well, it's really difficult to say whether it's going to be stagnation or not, because it's a little bit more difficult to understand the levels here. Anyway, here we have this surface for 4 years only, probably 5 years, but this is just the data which is given by my college. However, I found another picture in an internet, and this is another yield curve surface which extends to 19, or actually 2010, I guess. So let's look at an extended version. So this one looks like that. And now I think we can, just looking at this surface, we can say that we essentially see how investment community assessed future economy in different years. So it's a kind of history of economic or investment community thoughts and ideas about the future over many years, actually over 2 decades. So let's look at it, and clearly we see some patterns. So, for example, what we can say about volatility? So we have long ends, we have short ends here. So compare volatility of long ends and short ends. So you see that long ends yields or long ends interest rates are less volatile, and they than short ends yields or interest rates. And also the other, the major or the most important notes here is, or points here is that indeed all of them are declining. So long ends is declining, short ends is declining. Actually, up as early as 2010, short ends yields were already quite very close to zero. It's not still zero, but it's very close to zero. And that's what we observe nowadays. Nowadays, they actually got yields became less than. Well, in the UK, for example, the latest case is the UK in 2020 in June or in May 2020, the UK issued negative yielding debt, government debt. So that's our new reality. That we have either extremely low interest rates or even negative interest rates. So this is something which is our reality. But compared in 1990, yeah, 1990, somewhere here, short-term interest rates, for example, up to 1 year, interest rates with up to 1 year maturity has an amazing 8%. I mean, the value of these interest rates were 8%. This is something so unusual nowadays. It's probably even hardly imaginable that short-term interest rates could be 8%. So nowadays, this is just really difficult to imagine this. But that's used to be like that in 1990. Okay, so that's it for this lecture, for this topic today. I think there is nothing here. So this all is about discount function. So one home assignment will be about this, and you already have one home assignment. Now let's see how much time we have. So we have enough time. Let's move to another topic, which is absolutely different. It has nothing to do with this one because I would like to introduce a little bit of diversity for today. So I will stop demonstration here and I will switch to another slide. So where do I have it? Wait for a while. Mhm. Okay. Mhm. Okay. So this is a new presentation now, and we can start with this concept. So the concept of duration. This is one of the major concepts, especially not only in the theory of finance, but in practice as well. And later we will see why it is important. So some students probably have heard about duration or even have studied duration in their undergraduate courses. But anyway, I will just start with the very beginning. So let's discuss duration, and I will just give a little bit of introduction. So when we talk about bonds, some say that bonds are risk-free assets compared to stocks, for example. When they actually say this, they probably mean that bonds, especially government bonds, treasury bonds, they are default free, especially we're talking about developed countries and advanced economies. So indeed, there is no such risk as default risk for these bonds, but it's not still correct to say that bonds, even treasury bonds, are risk-free securities. This is not so because even though the default risk is equal to 0, there is another risk, and you all know this risk. This is price risk. We discussed price risk in the first lecture, so we can say price risk, or we can say interest rate risk. Anyway, this is a risk that the interest rates suddenly will go up, and then as a result, the price of the bonds goes down. So if a bond has a price risk, then it's a good thing somehow to measure this risk. Recall that in the very first lecture, we measured price risk in terms of compensation, which is required for bearing this price risk by investors. So we measured government spreads, difference between medium-term and short-term yields, or between long-term and short-term yields. So this is called government spreads, but this is an indirect measure of price risk, because we essentially measured not the price risk itself, but the compensation which is required for this price risk. However, if we want to measure price risk directly, just like, okay, so we have this risk, how can we assess this? Then we are going to use the duration concept. So once again, you all know, by now you all should know that there is an inverse relationship between bonds prices and bonds yields. So when bond yields go up, bonds prices go down, and vice versa. When yields go down, bonds prices go up. In our case, the adverse situation, the unfavorable situation, is when bonds prices go down. As a result, when bonds yields go up. So, or when the general level of interest rates go up, then bonds prices go down. So if this happens, we might end up with the portfolio of bonds having less value than our initial investment. So that's probably the worst situation. And if this occurs, then this is where price risk is realized. That is, we have this negative consequence of price risk. So just knowing that bonds price goes down when bonds yields go up is not enough. Okay, we all know about this right now, but how will it help us to, I don't know, to assess the risk of the portfolio? So just knowing that there is an inverse relationship is not enough. We need to know something more. In particular, we would like to know not just that the bonds price goes down if interest rates go up. The question is by how much the bonds price goes down if interest rates go up. So that's a more important and more precise question. So essentially, we want, technically speaking, we want to know by how much the bonds price changes with respect to a change in the bonds yields. So I would say with this, by how much the bonds price changes with respect to a small change in bonds yields. Does it remind you something from mathematics, some concepts or something like that? So a change in the bonds price with respect to a change in the bonds yields. Right, this is essentially a first order derivative. So recall that in mathematics we say a change in the independence variable, change in the dependence variable with respect to an infinitesimally small change in the dependent variable. In our case, but this is mathematics. In finance, we don't say, we do not operate with such a notion as infinitesimally small change because it makes no sense in finance. So I would just say small change. Okay, so we can say a change, we would like to know a change in the bonds price with respect to a small change in interest rates, something like that. Anyway, interest rates are unlikely to change by infinitesimally small amounts, so this just does not occur in real life. So this is simply the concepts of the first order derivative, and that's what we are going to use. Actually, there are well, to my knowledge, there are 5 or 6 measures of durations which can be used in practice, and I'm going to give you 3 measures. We're going to discuss 3 measures of durations, probably the most frequently used, but all of these measures are based on this first order derivative concept. And let's start with and by the way, mind is that duration is a measure, not is a measure, it's a concept or equation in the CFA level 1 exam. So if you are going to hold it or take it, then just pay attention um, to this lecture. So anyway, we'll start with the simplest measure. It's called duration, dollar duration. Let me switch on the marker. And dollar duration is just the first order derivative. So this is our first order derivative, a change in the bond's price with respect to a change in the bond's yields. So what you should pay attention here, in the numerator we have change in the price in dollar, meaning it can be in dollar, in British pounds, in ruble. Anyway, it's a money change measured in money. What we have in the denominator, mind it that here we measure change in percentage points. Here sometimes students get confused because they just don't understand what the difference between percentage points and percent. So for example, 1 percentage point and 1%. And this confusion comes from the fact that, so for example, we say 1%, 2%, 3%, it's okay. But when we say percent, we actually mean relative change, not absolute change, but relative change. But interest rate itself is already measured in percent. So its percent is its unit of measurement. So then what units should we use in order to indicate that this is going to be an absolute change, not a relative change? So for example, from 5% to 6%. So if we want to measure an absolute change, 6 minus 5 is equal to 1. So we say 1 percentage points. So this is an absolute change. It is measured in 1 percentage points. So in order for you to understand it, or in order for me to see that you understand it, let's assume that we have 10% interest rate, then it changes to 11%. Tell me what will be the absolute change and what will be the relative change. So from 10 to 11. Right. So an absolute change is measured in percentage points. So we would say that interest rate would change by 1 percentage points. But if you want to assess in relative terms, using exactly percent in its right definition as a relative change, as a measure of relative change, then you would say that interest rate would change by has changed by 10%. Anyway, here we have absolute change. So we have absolute change in the numerator and we have absolute change in the denominator. But anyway, this is just the first order derivative. This is our formula for the bond's price, and therefore we are going to take the first order derivative. So this is something which all of you should know how to do. There is nothing difficult about it. So you will do that at home. You should do this at home. But anyway, as a result, we have this. So this is the first order derivative of this formula. So what we see here, well, nothing particular, simply just some formula. Mind it that we get minus here. So tell me please, is that what we expect, that we get? So duration is essentially negative, right? Because all other terms are positive here. There's no negative terms because all cash flows and times and yields, they are all positive. So the duration is going to be negative. So is that what we expect? Or tell me please, what do we have negative term here? So do we expect that duration is going to be negative? would you not expect? Right, indeed. So with increasing yields, price falls. So it means that we anyway have an inverse relationship, and that can be seen from the formula. So therefore, the first order derivative is going to be negative. So it just points out to this negative or inverse relationship. So the downward slope, there will be downward slope, and this derivative indicates this downward slope. So this minus indicates this downward slope. Well, that's always fine. So essentially, it will tell us if the interest rate goes up by certain amounts, then the price would go down by certain amounts. It's always fine, but this derivative has, but actually, I think I have a example here. Let me see if I have an example. Yes, I have an example here. So assume that we have a coupon bond. It has 10% coupon rates, well, annual compounding for simplicity, 5 years time to maturity, and 5% yield to maturity. So how to calculate duration? Well, if you do it in Excel, you'll just do it like that. I mean, obviously, you can do this using formula in Excel or even in some online calculator. However, if you want just to reproduce all the calculations in Excel, then you will get something like that. So you need to calculate all cash flows, that is CTN. So this CTN, all cash flows, then yield is given, then you calculate present value, that is you take cash flows, you divide by yield to maturity raised to power, so you get present value of all the cash flows. Then you calculate the bonds price. So the bonds price is going to be equal to 1,216. And then you do not forget to multiply by t. So you get something like that. And then you, well, you divide it by this. So anyway, this all just is really easy. You can do this in Excel. And the result is something like that. So minus 4,928. So how can we utilize this number in order to understand by how much the bonds price changes with respect to a change in the yields? So we assume a small change in the yields, not infinitesimally small, just small. For example, 1 percentage points from 5% to 6%, from 10% to 11%, etc. So you simply need to multiply duration by the actual change. Do not forget that actual change should be converted to decimal points, to decimal number, or actually this is decimal fraction. So you convert it to the decimal fraction, you multiply, and then this is the amount which you get. So the price, if interest rate changes by 1 percentage point, then the price will change by about $49. Do not forget that if change is positive, like here the change is positive for the yield goes up. Here we have negative change for the price goes down by about $49. Okay, so it's always fine about dollar duration. However, it is of limited application. There is one thing which makes it very inconvenient. So let's look back here. So what is inconvenience about using the dollar duration? Will you tell me? I try to guess. This is something about the numerator. So Okay, right. In the numerator we have change 1 minute. Neutral measure. Well, you definitely are not talking about risk neutral probabilities, aren't you? It's just a neutral measure, you know. I don't quite understand. Risk neutral measure or what? It doesn't measure risk properly. Well, it measures, but it's of limited application because, well, you're saying need to calculate the modified duration, but you do not say why. We have currency. So, all right, so we have currency in the numerator. It means that it will tell us by how much, well, by how much in money terms the price changes. This is okay if you just want to analyze one particular coupon bonds. But if you want to compare different durations among different bonds, essentially when you compare durations, you compare a measure of risk. So actually the measure itself is correct, but it's not comparable because, for example, if we take the UK bonds, then its face value is equal to 100. In the UK, the face value is equal to 1000. Therefore, a change measured by dollar duration will be quite larger for the UK or for the US bonds than for the UK bonds. It does not mean that the UK bonds are less risky and the US bonds are more risky. It's only just it's just because of different face values and therefore different prices. Because the face value is 1000, it means that the price, the market price, will be somewhere near 1000, but definitely not near 100. Therefore, it's just this measure does not allow to compare bonds among one another. Tell me, please, what we need to, we slightly need to change this in order to adjust this formula, in order to allow for comparison among different bonds. So tell me, please, what adjustments do we need to introduce in order to allow for comparison? Try to guess. So our major problem is that we just cannot we get a change in the price in absolute terms, in money terms. So what should we need to introduce? Right, exactly. We need to somehow to express the numerator in percentage terms, in relative terms, rather than in absolute terms. So how to do this? For this, we are going to use modified duration, and modified duration is dollar duration modified. Okay, let me say it like that. So we introduce only one modification. Let's look at this modification. So modified duration. Okay, this is our dollar duration. What we do, we simply divide by the current price, the original price of the bonds. So essentially, we express a change in the bond's price relative to the original price. So essentially, we represent this change in relative terms or in percentage terms. So this is the first modification which we introduce. But there is one more modification. As you can see, we explicitly put minus here. Recall that duration, this is our dollar duration. Recall that it's always negative because all these terms are positive. And then we have minus because of this inverse relationship. So essentially, it's because of this t. When you take the first order derivative, you will get minus as a result. So our dollar duration is always negative. But then in modified duration, we multiply dollar duration by minus or by minus 1. Therefore, we artificially make modified duration positive. So the logic behind this, that we divide a change in the price by the current price, is understandable. We want to express a change in the price in relative terms. The logic behind this is not quite obvious, because the question is, why do we make it artificially positive? Well, my guess is, I mean, I have never seen any clear answer why it's so. So, I mean, it can be minus, it can be plus. So it just doesn't make particular economic sense, in a sense that I assume that we make artificially modified duration positive in order, just because we don't like negative numbers. Economists like positive numbers more. However, even if as a result you get positive number, modified duration is going to be positive, even in this case, you should always bear in mind that we're talking about an opposite change. So if yields goes up, price goes down. If yields goes down, price goes up. So even though we have positive number as a modified duration, when we apply this to calculate a change in the price, means it's that the change in the price will be in the opposite direction. So do not forget, bear this in mind. So now we have change in the price in relative terms, and the denominator does not change. So essentially, the only adjustment is that we divide by the current price. So this is our dollar duration. Minus cancel each other, and therefore we also divide by the price. So this is our formula for modified duration. And here is an example. So that's the dollar duration. This is a continuation of the example. So this is our dollar duration, which we calculated previously. And then recall that the current price was this one. So we divide it, and then we get 4.05. So this is the value for the modified duration. As you can see, it's positive, but you should understand that if interest rates increase, the price decreases. So by these amounts in percentage terms. Okay, so that's it about modified duration. Let me check how much time we have. Not much. So dollar duration is done, modified duration is done. Let's introduce to you one more duration, which is called Macaulay duration. Well, probably you heard Frederick Macaulay, one of the influential economists in the first half of the 20th century. Anyway, he introduced this duration, and now it's called Macaulay duration. In order to calculate Macaulay duration, you use modified duration, and you modify it even more. So let's see what kind of modifications you introduce. So the numerator is the same. So we have change in price in relative terms in modified duration. So it's still the numerator. I'm not sure if you can hear me, because I'm sad that my wireless is not stable, but I guess you can hear me. Okay, I will continue. So no change is introduced in the numerator. However, if you look at the denominator, we have an dy, that is net change in the net yields. We now measure change in the gross yields, and it's not just dy, it's divided by the gross yield. So essentially, this is a change in the gross yields given in percent. So we have relative change in the numerator, and we also have a relative change in the denominator. And do not forget about this minus. Just like in case of modified duration, we also multiply by -1. So we do have Macaulay duration artificially positive. And here is an example again. So our modified duration was equal to 4.05. And therefore, between Macaulay duration and modified duration, so you get 4.25. And now the last concept. Okay, I just have 5 minutes, just enough. So it's all fine with duration. So you know Macaulay duration, modified duration, and dollar duration. again, in the CFA exam, you might be asked about the differences between these durations, so you somehow need to explain it. Now, this slide is easier, so just you will read it in lecture notes. I would like to, and here we have again an example. So let's move to the next concept, convexity, which is related to duration. So so here we have dependency between the bond's price and the bond's yields. I remind you that this dependency is inverse. An increase in the bond yields means a decrease in the bond's price. So, and obviously this dependency is non-linear because you see this formula. Where is the formula for the bond's price? Okay, this one. So anyway, you see that the relationship is non-linear, so we were supposed to have some curved line, and this is our curved line. So we assume that this kind of curved line explains or describes the relationship between the bond's price and the bond's yields. And now duration. So we're now talking about dollar duration. So recall that dollar duration is simply at the first order derivative. So it indicates the slope, as a slope to the curved line at this particular point. So if we are now at this yield, so this is our current yield, yield to maturity, and if we want to estimate by how much the bond's price will change in money terms, because here it's expressed in money terms. So if we want to estimate by how much the bond's price will change if yields increases, for example, so it goes in that direction, so then we just might use simply the first order derivative. We look at the rate of change. So derivative is the rate of change. So we'll look at this. So somewhere at close proximity to the initial yields. For example, this is our new yields. I'll just use this yields prime sign. So we'll just go like that. And that will be our new price. So it used to be at this level, and now it's going to be at this level. So we estimate a change in the price using this duration concept, using this rate of change measure. So we would say that the new price is at this point, but if we would actually calculate the new price, then it would be at this point, right? So we just use this curved line. As you can see, the difference is not really big. I would say that our approximation would work very well. But now let's assume that a change in the yield is much larger. For example, we are at this point. So a very big change in the yields. And now using the same first order derivative concept, we would say that our new price has dropped to that level. But actually, the price has dropped to this level, which is much higher. Why? Why do we have? And you can see this mistake increases compared to this mistake. Here it's just negligible, but here it's quite large. So why do we have this mistake? It's simply because this relationship between the bond's price and the bond's yields is not linear. So when we approximate it using a linear relationship, we might be mistaken, especially if the change in the yield is quite big. So we take into account the first order effects, but we do not take into account the second order effects. And the second order effect is this curvature. So the yield has a curvature, and because of this curvature, a change in the price will not be that drastic as the one estimated by duration only. So if we want to be more precise, we need to introduce one more concept, convexity. So we need to take this into account. So how to take it? Obviously, we just calculate convexity as in mathematics. This is the second order derivative, right? So convexity is measured by the second order derivative. But if we want to measure convexity and duration among different bonds, then we need to divide convexity by the current price, just as we do it using with modified duration. Otherwise, we won't be able to make this comparison. So we divide duration by the price, to make a change in relative terms, and we do the same with convexity. So we divide by the price. And now the last question, and I don't know, I will just take a couple of minutes, not more. The last question is, if we want to use both duration and convexity, so that we know how to calculate modified duration, we know how to calculate convexity. The question is how to combine duration and convexity in order to use these two measures together to better estimate a change in the price, so to better estimate price risk. And here we are going to use one concept. So once again, this is our this is the curved line which describes non-linear relationship between the bond price and the bond yields. And we are going to do something similar to what we did before. We are going to approximate this curved line with another curved line, which is easier in a sense that we can manipulate it with easiness, unlike with this original curved line. So we are going to approximate this unobservable curve using this approximation. And we are going to use again polynomial, but actually in this particular case, we are going to involve such a concept as Taylor series approximation. So for those of you who don't remember what it is, I advise you to to refresh your knowledge on this, because we are going to use it more in the future. But anyway, Taylor series approximation looks like that. Okay, you can actually use Wikipedia probably for this. That will be enough. Just refresh your knowledge on how it looks like. You don't need to prove anything. So we're going to essentially estimate this function, approximate this function using seconds order. So here we have seconds order Taylor series approximation. So this is our original function, and this is our bonds price, and this is our bonds price function. So how we are going to approximate it? So if you do all these mathematical calculations like that, you will essentially come to this final solution. So this is modified duration, and this is convexity. So if you want to use both convexity and duration, then you should use something like that. Okay, I don't think that I can take more time from you, because that's it for today, 20 minutes. So, all right, that's it for today. And if you have any questions, you may ask. If you have no questions, I can let you go. And if you have questions, you may ask. Okay, that's good that you liked it. Don't be afraid by this mathematics, and because it's really easy, especially when you know these concepts. And moreover, my advice to you, be prepared for more mathematics. So anyway, start with studying this Taylor series expansion concepts. Okay, have a nice evening. I guess you don't have any questions. So have a nice evening and have a nice weekend. No, you do not need to submit. Next week we are going to have home assignments. We are going to have a tutorial, so we will consider the home assignments which I assigned to you this week, or probably even last week. So it's about annuity and yield curves. And also tomorrow I'll send you lecture materials, and I'll send you home assignments for the tutorial which will be 2 weeks from now. Okay, so have a nice weekend. Goodbye.